Today's problem is rat in a maze, difficulties medium, accuracy pretty low. Um, it's um, it's just the concept is simple. It's kind of hard sometimes to to keep it all in your to keep it all in your mind and get every piece of it right the first time. So that said, here's the problem. Consider a rat placed at position 0, 0 in an n by n square matrix called maze. The rat's goal is to reach the destination at position n minus 1, n minus 1. So going from the top left corner to the bottom right corner, the rat can move in 4 possible directions: up, down, left, right. The matrix contains only 2 possible values. 0 is a blocked cell through which the rat cannot travel. 1 is a free cell that the rat can pass through. Your task is to find all possible paths the rat can take to reach the destination starting from 0, 0 and ending at n minus 1, n minus 1, under the condition that the rat cannot revisit any cell along the same path. Yeah, that makes sense. Otherwise, you've got like infinite number of solutions. Furthermore, the rat can only move to adjacent cells that are within the bounds of the matrix and are not blocked. If no path exists, return an empty list. Return the final vector in lexicographically smallest order. All right. Well, it's a little bit hard to see what's going on here in the absence of a diagram, but you can see what the format of the output is going to be. So the rat, in this case, is able to get through this matrix by going down, right, down, right, right. One other possibility as well. This one has no solution, 2 possible solutions, and cannot be very big. It's going to be between 2 and 5, which is good because if you use a backtracking algorithm for this, the runtime is not going to be good. So if you have a maze that's like 1,000,000 by 1,000,000, I think there actually is on LeetCode a problem where you're trying to get a rat through a huge maze, not to find all the paths, but just to find if there is a path. And then in the maze, you have zeros and ones. Okay, here's the expected complexity. It's pretty bad. 4, well, 4 to the power of n squared. Well, that makes sense because the number of squares is n by n, and you have 4 possibilities for each square. Auxiliary space n by n. We're going to use that to keep track of which cells have been visited so that we don't revisit them. Topic tags, backtracking. All right. So let's take a look. I mean, the concept is easy. The rat starts at the top left corner, and the rat will try to move in 4 possible directions: down, left, right, up, from every possible square. Yeah, so that's it. We have an array list that is going to contain our solutions, an array list of strings. The maze, if the 0, 0 square contains a 0, meaning it's blocked, there isn't going to be any solution. So we might as well just handle that as an edge case. N is a class variable. That is the length of the maze. Visited, it's defined up here as a class variable, and it is an n by n matrix. So if we define it like that, it's going to be initialized to zeros. We're going to use 1 in the visited matrix to indicate we've already visited this square. Maze, we're going to put that in a class variable. All of these really could be passed as parameters, you know, to the recursive function here, solve maze. But I prefer to use class variables where they seem to be appropriate rather than like having 7 parameters going into a method. All right, let's see. Okay, and then we do the call to solve maze. The initial parameters are the position of the rat, which is 0, 0, and the path, which is initially an empty string. So we'll take a look at this. di and dj, if you want to think of that as delta I, delta j, those are the changes to the I and j index. Those are all the possible changes, and those correspond to these letters right here. So if we add 1, for example, to I and leave the j unchanged, that is going to move us down. If we leave the I and subtract 1 from the j, that will move us to the left, and so on. So these changes to I and j correspond to moves up, down, left, right, up. All right, whatever square we're on, we're going to try to move in 4 possible directions. So that's why we have a loop from 0 to, well, really to 3. And we'll create the indices of the square that we want to move to. So I plus delta I, j plus delta j. This big long thing here, I sort of thought about putting that in a separate method like an is allowed method, but here it is all in the if statement. The first 4 checks here are checking that I and j are in fact within the bounds of the array. The next check is that we have not already visited the cell that we want to go to, and the final check is that the maze at the cell that we want to move to is a 1 and not a 0. If all that's true, then we're going to update the visited matrix to 1, and we're going to do a recursive call to solve maze. Input will be the next I and j coordinates and the move string plus the direction that we're moving in. Okay. Well, this is going to generate a series of recursive calls which will eventually unwind successfully or unsuccessfully. But whatever happens, when it does unwind, we're going to backtrack. So we're going to set visited at these inputs here. We're going to set it, here we set it to 1, and we're going to set it back to 0. So that is going to allow us to either go to the next of the 4 possible squares that we can move to from this cell, or if we've moved to, if we've tried all 4 of them, then it'll backtrack us to the previous index. Okay, so that is it. And let's try and submit it. All right. I actually submitted it once by mistake because I kind of lost track of where I was on the puzzles and the time. I didn't think that I thought it was yesterday's puzzle, and it wasn't. So I always like to include getting the geek bit in the video if possible. So I did get the geek bit, but it's not going to be in the video. Oh well. I encourage you to like the video anyway, and subscribe to the channel for daily problems of the day, daily on weekdays, and we will see you next time.